So the alcohol naming is very similar to the alkene naming with some minor changes because the functional group is different. So the first parent chain must have the OH group, hydroxy group. By the way, the naming organic compound, since now we have covered quite a few functional groups in detail. Among the different functional groups, when we name compound with multiple functional groups, there's a hierarchy that we organic chemists consider to name the compound. So for example, the carboxylic acid is one of the higher in the hierarchy, whereas the OH group, hydroxy group, it is lower in the hierarchy. So just be aware of this. The alcohol, it is higher in the hierarchy in our naming, higher than the alkene. So when the compound have OH group, we focus on the longest parent chain must have a hydroxy group so far. And we must keep the hydroxy group as low number as possible, the low count as possible. So that's basically to set a tone for naming the compound. And so let's see some examples. There's a lot you can read, and this is the example. This is kind of simplest. We have a single chain with no substituent except the hydroxy group. So you name as based on how many carbon, that's 5, so it's a penta. And you have the position 1 have OH, so simply just name as a pentanol or 1-pentanol. Okay, 1-pentanol. And so like this kind of example shows you the parent chain must have OH group, not necessarily the longest current chain. And so this shows you this compound name will be this will be position number 1 because we keep the lowest locant for the hydroxy group. Position 1, 2, 3, 4, 5, 6. So the last part of the name will be hexanol, and it's a 1-hexanol. Position 2 will have a propyl group. So this name will be 2-propyl, 1-hexanol, such as this. If there's more than one functional group, such as bond, hydroxy group is higher in the naming hierarchy. So the named compound will still need to keep the longest chain with hydroxy, give the lowest number as possible instead of the double bond. So that's quite a difference. In the alkene or alkyne, we give the double triple bond as a low number, locant as possible. But when you have OH, since the higher hierarchy, we'll keep them lower, lowest locant. And so this compound name will be a enol. Okay, it is actually en and alcohol together is the enol. All right, so that's the RS designation still applies. RS designation still applies. And that's the same as we learned before, no difference. And so the alcohol locant for the hydroxy group can be either before the parent, before we name the parent chain, or in the middle of the parent chain. That's the same as alkene. Okay, there's no difference. Okay, there's a little difference because we name the alcohol, the parent is the alkane, no unsubstituted, no unsaturated functional group. So the parent is actually pentane. Okay, pentane, pentanol. If the parent chain has double bond, then would be pentanol. So anyway, so far we don't see the pentanol, we only see the pentanol. And so that's difference. When we name the alcohol, put a position either before the parent or right before the OL, which means the position for the hydroxy group. So that's basically the either or. It's very similar to alkene or alkyne. The alkene alkyne, you can put the location of the double or triple bond in the middle of the name or in front of the parent name. So that's the same. And this is example shows the chiral molecule. You got an RS configuration, and you can see the we treat the benzene ring as substituent. So this is phenol group, chloro group, and we give the OH as the lowest number as possible. So the position 1 has OH, and so just name such as this. Alphabetic order. This is phenol, start with P, and the chloro start with a C. So this is go name first. Okay, so naming the alcohol doesn't really nothing much new. It's very similar to the alkene or alkyne. Cyclic alcohols naming is fairly straightforward because there's no if there's only one OH, then the OH group on the carbon, this carbon name was number 1. And based on this, we still need to give the next substituent as small as low number possible. So for example, this one's carbon number 1. And we can either go the clockwise to the numbering, or not clockwise goes this way, or counterclockwise go the other way. And you can see the counterclockwise gives the 2-methyl group as a lower number than the clockwise. So we named, put a number in the counterclockwise manner, start from the position 1 as with OH group. And so there's some compound we actually give a common name. So for example, this is a rubbing alcohol, the alcohol component in the rubbing alcohol. Rubbing alcohol is basically an aqueous solution of isopropyl alcohol. And so the proper name is supposed to be the 2-propanol, or propane 2-ol. So the 2 ways to name the compound. And this is terbutyl. When you learn about the T-book, which is the terbutoxide, the conjugate base of the terbutanol. So you can see the terbutanols actually come from this. Either terbutanol or terbutyl alcohol. Terbutyl alcohol. And the proper name also goes the 2-methyl 2-propanol. Okay, position 2 has a methyl group. This alcohol, it is actually a phenyl methanol. But this entire group in organic chemistry, we oftentimes call the benzyl group. This is benzyl group. It's benzene ring with methylene, or the methylene CH2 attached here. So that's become a group, the benzyl group. So the name we call it benzyl alcohol. The proper name is phenyl methanol. The alcohol, similar to the carbocations or the halides, there are different degrees, and the definition is exactly the same as how we name the halides. When there are more substituent on the alpha carbon, okay, alpha carbon being the carbon linked with the connected with the hydroxyl group, the more substituent, you get higher degrees of alcohol. As we have seen that before in the elimination reaction, substitution reaction, those tertiary alcohols tend to go through the SN1 reaction and so forth. So that is we've seen that before. The phenol naming is different. Again, the benzene ring with the carbon that is linked with hydroxy group, that's number 1 carbon. And based on the number 1, we can name the other groups. And again, same principle. We keep the substituent as a low number as possible. So this is the parent name is the phenol. And this is position number 1. And since the nitro group, this we call nitro group, bound with a second next to the number 1 carbon. So this will be number 2, because pick this number 2, naming clockwise, the numbering clockwise will keep the substituent as low locant as possible. So number 2, number 3, number 4. Number 4 has a chlorine. So that's how we're going to name for the compound. The other way to name the compound is OMP system. The OMP system, most likely you will see in the next semester, organic chemistry, the OMP system. The O means the position 2 have substituent. This will be the O position. And the position 3, if 3 has a group, that'll be the M, meta. O is for also, M for meta. And the position 4 is a para position. Position 4 is a para position. That's for the OMP system. And the OMP, so basically that's how we named it. Instead of giving numbers for the substituent, we'll give the OMP a simpler system to name the compound. So the O-methylphenol, it is also the 2-methylphenol. The M-bromo, M-bromo is a 3-bromo phenol. And position 4 has isopropyl group, so that's the p-isopropyl phenol. So that's how we name the phenols. It has both name, the number. When you have more than one other substituent in addition to the hydroxy group, it's better go with number. But when you have only 2 substituents, one is the hydroxy group, you just need to signal the location for the other substituent, which is either O or M or P. So that's 2 naming system, and both are legit. So this is about little basic introduction about those alcohols in our everyday life, in our civilization. The methanol is the simplest alcohol and mainly come from the carbon dioxide and the hydrogen gas every year. The methanol is a very volatile alcohol. It's probably the most volatile alcohol because of low molar mass, and it only has one OH group to form hydrogen bonding. And so the methanol is actually massively produced. In some labs, they actually use the methanol for cleaning, but the vapor methanol can cause blindness. So ethanol is, of course, very commonly used. It's massively produced. It's also food for the alcoholic beverage have ethanol. Isopropanol is basically rubbing alcohol, and they use for industry. The alcohol's basic physical properties. First, they have OH, so they can form hydrogen bonding, and therefore it is more tend to be water soluble and have a higher boiling point, and so forth. The solubility of the alcohol really depends on how long the alkyl group is, because OH group is polar, but when you have a very big, bulky alkyl nonpolar group, then the molecule will have a less poor solubility with water as the alkyl group becomes bigger. And so the general patterns, alcohol with 3 or less carbons are generally miscible with water, means any ratio with water. Start from butanol. The alcohol, because it's a bigger nonpolar alkyl group, it becomes less soluble in water. And the alcohol can be used for antibacterial because it can denature the protein. So it can change the protein structure, make the protein in the bacteria unable to function and to kill the bacteria. The alcohol is a protic compound, and so it's very acidic. The acidity of the alcohol is very similar to water. It's a little bit less than water, not by much. And so the alcohol, we can use some strong base. The base that is stronger than sodium hydroxide will deprotonate the hydrogen from the alcohol, give you the alkoxide, which is a very strong base, and many of them are very strong nucleophile. So as we learn in the elimination reaction, substitution reaction, those are alkoxide, very popular. And so the acidity of the alcohols we can decide based on the ARIO, the atom, resonance, induction, orbitals. These are the four factors we compare the acidity. So this we've seen it before as electronegativity increases from hydrogen from the carbon. This is carbon, and this is nitrogen with hydrogen. Increasing electronegativity causes stronger acidity. So there's nothing really new about this. pH. The resonance, okay, phenols, they are even more acidic than alcohol. As you can see, the cyclohexanol pK is 18. A phenol pK is only 10. So that's about 100 million times stronger than the structure is similar to alcohol because of resonance. So once the phenol depronate from the phenoxide ion, it can have the resonance, and the negative charge can be dispersed among several carbons. So basically, through the resonance, the negative charge will be distributed among those sites. And the dispersion or delocalization of the negative charge helps stabilize the phenol site. It's even more acidic. And there's a question about which compound can deprotonate the phenol. So basically, it has to be a strong base to deprotonate. And so, for example, this alcohol pK is 18. The deprotonation reaction, this is kind of I couldn't go over that, but in the acid-base chapter, we discuss if this reaction moving forward or not depends on the pKa of the acid. This is the we have a you have a reactant acid, and once deprotonate, there's a product acid. So basically, compare these two pKa. Compares these two, which are stronger acid. If the reactant acid is stronger than the product acid, then the reaction will be favor the product. And so that's basically what I learned before. I will not spend time to discuss here, but that's basically what kind of boiled down to. The water pK is 15.7. So depends on this acid. This HA has to be stronger acid than water, so that this equilibrium will shift to the right hand. And so which means that this pK must be smaller than the water, 15.7. Between these two, you can see only the phenol. Phenol gives us a smaller pK or stronger acid than water. So therefore, only the phenol will have this reaction. Phenol will be able to be deprotonated by hydroxide to form phenoxide. And so basically, sodium hydroxide is not strong enough base to deprotonate normal alcohol. Okay, we need something even stronger base to deprotonate alcohol. So there's some other factors. Induction effect we learned about before. The stronger electronegativity atoms can pull the electron away and make the alcohol more acidic. This is a good example. This is the trichloroethanol, and this is the same methyl group, methylene group. But when you have the next, instead of methyl group, we have a trichloromethyl. This is a strongly electronegative chlorine pull away the electrons from the carbon. So that helps stabilize negative charge on the oxide anion. And that's why the trichloroethanol gives you stronger, more acidic than the normal alcohol because induction effect. The solvation, the solvent also affects the acidity. So this is where you find a smaller alkoxide ion, such as the methoxide or S oxide. better stabilized by polar solvent. As a matter of fact, only the polar solvent dissolve those alkoxide anions. And the solvation effect, it cannot be quite explained by the ARIO, which is only the molecules themselves. Because outside environment also affect the stability of the anions. So the predicted acidity of the alcohols, I'm have to skip this exercise because in our lecture and also the future homework, there won't be much that dealing with acidity of the alcohols. It comes from the old exercise in my older PowerPoint. Okay, so today's lecture will focus on the synthesis or preparation of alcohols. And there are many reactions that can form alcohol. So here's a quick review. In the chapter 7, substitution and elimination reactions, we learn about substitution reactions from the alkyl halides by either base hydroxide, the stronger base hydroxide, or the weak base water. And it goes through the substitution reaction to give us alcohol. It can be either SN1 or SN2 mechanism. The SN1 typically uses a weaker base. And as we recall the tertiary alkyl halides, it'll go through typically the SN1 reaction to form alcohol. And the primary halides will go through SN2 to form the alcohol. So that's the use of substitution reaction in the chapter 7. Chapter 8, when we study the reactions of alkene and mainly addition reaction, we have seen there are quite a few reactions to form alcohol. And from the alkene, because the alkene can add either directly with water, with catalyst, or go through some mercuration, demercuration, or hydroboration reactions. And so those reactions, there are 3 different ways to form alcohol, have different residual selectivity. So first go over the substitution reaction. Substitution reaction, the primary goes through the SN2 substitution. It needs to be stronger base. Hydroxide is necessary because it's SN2 reaction. The attacking of the nucleophile, the strength of the nucleophile is important in the SN2 reaction. Tertiary alkyl halides go through the SN1 reaction. And so the first step forms the carbocation. And since the carbocation formation is more important, and the following water nucleophile attack the carbocation is a fairly quick process. So don't need a strong base. And actually for tertiary halides, if strong bases are present, oftentimes lead to elimination product, as we learned before. And so that's the use of substitution reaction and the reaction mechanism that we learned before. The alkene hydration reaction, it actually has 3, as we just mentioned, there are 3 different pathways for the hydration. Adding water, okay, quote unquote, adding water to the alkene, have 3 different pathways. And they have a different residual selectivity, which means which location depends on what kind of carbon will attach the hydroxy group. That depends on what reaction process. The simplest, which is actually the least used, it is acid catalyzed hydration. And this reaction form a carbocation. Is a form of carbocation, so it's prone to rearrangement. So when you see those kind of rearrangement, oftentimes inorganic synthesis, we try to stay away from because they lead to some product maybe not as we planned. So that's the method one. Method one is the acid catalyze, form the carbocation intermediate. This reaction, by the way, if there's no rearrangement, the residual selectivity we call the Markovnikov is with OH group attached to the carbon with more substituents, with more alkyl groups. So both are Markovnikov. Okay, very soon we're getting to discuss about synthesis. Now we have to think about what reagents to use to form product. This use the mercuration, demercuration. Demercuration use the sodium boron hydride. This reaction, because not going through carbocation, so it's not subject to rearrangement, no rearrangement. Okay. The third reaction, because the third reaction is hydroboration oxidation reaction. This reaction gives anti-Markovnikov with OH attached to the carbon that is less substituted. And so you can see these three, it depends on what kind of product we want to use. We can choose really. In synthesis, these two are the most popular. Try to stay away from the carbocation because it can lead to rearrangement. And there are more ways to make an alcohol. This is actually the main topic in today's lecture. Alcohol can be made from the reduction of a carbonyl group. And the reduction can be two ways. The reduction in general chemistry, the original definition of oxidation reduction is oxidation will be the reaction, a compound reacts with oxygen gas, and the compound will gain oxygen because of this reaction. That's oxidation. Reduction is the process that removes oxygen from the compound. Either remove oxygen, actually remove oxygen, or we add a hydrogen to the structure, and that's also we call it reduction. And so by adding hydrogen, we can add hydrogen on the both two atoms, which was unsaturated before, and now have an alcohol. And adding hydrogen, there are two ways. One is the hydrogenation. This is basically use hydrogen gas and the catalyst to react. And we've seen that before, very similar to the alkene reaction. The other reaction, this is kind of unique, is a reaction with hydride, the negative charge hydrogen ion. This reaction also can give hydrogen to the structure. The reason why we can use hydride because carbonyl is a polar group, and with high electron activity on the oxygen that has negative charge, carbon's positive charge. So the carbon, it is electron deficient. It is an electrophile. And so if a reagent that has hydrogen and is nucleophile, then that can react. And therefore the hydride is oftentimes chosen for the reaction. So the first one, we talk about the catalytic hydrogenation. Add a hydrogen gas to the carbonyl with a catalyst. This is a reaction very similar to the alkene reaction. This reaction need a high temperature and high pressure because the hydrogen is a fairly stable molecule. And to make the reaction fast enough, we need a high temperature. This reaction is actually a entropy decrease process. And so since entropy decrease and there's exothermic, so supposedly this reaction is exothermic and the entropy decrease. And so when you have such kind of reaction, supposedly low temperature will be in favor of this reaction. Okay, entropy decrease because you can see the hydrogen gas diminish. You lose the freedom of the hydrogen, and the two reactants become one product. And such a reaction should be preferred at a low temperature, will be more preferred. But because high activation energy, we have to speed up the reaction. So high temperature has be chosen for the reaction to be practical. And the reaction is very simple, and there's not so much to discuss. We basically add hydrogen on both oxygen and the carbon, this carbon. The hydride addition reaction is more interesting, and the reaction mechanism is relatively simple. So the reaction can be a reagent that provide hydrogenated ion. So for example, the sodium boron hydride or sodium boron tetrahydride. And this is very commonly give you the hydride. This compound you can pretty much consider as a sodium hydride combined with a borane. These two come together. So you have this is a hydride. And between hydrogen and boron, hydrogen have a slightly higher electron negativity. So it's also a negative charge here. So that's give you hydride. And the reaction is fairly straightforward because hydride and negative charge give them, they are able to, the hydrogen will take the pair of electrons from the hydride compound. And this hydride takes 2 electrons, form bond with the carbon. Okay, the forming bond start with carbon, be the carbon's positive charge, hydride negative charge. And so you have a reaction produce a alkoxide. This is basically alkoxide anion, which is intermediate. And so this is actually ionic. To finally give us the alcohol, we need some kind of weak acid. So water or alcohol, they are weak acid, will be able to give protons to the alkoxide, eventually give us a product, the alcohol. So the reaction mechanism is very straightforward. And there's another hydride agent is a lithium aluminum hydride, LAH, whatever you pronounce it, LAH. This compound also is very strong, very good hydride provider. And this reaction, you first just add the reagents into the solution, and it will form the alkoxide ion. And the last step, use a weak acid to protonate the alkoxide. And so the reaction mechanism is all the same. Instead of boron, now have aluminum, and you have a similar mechanism. The product's the same, give us alcohol. Okay, so we need to, we have 2 ways to give hydride to the carbonyl and then produce alcohol. But what's the difference between the aluminum hydride versus the boron hydride? The aluminum hydride, LAH, is much more reactive because aluminum is metal, low electron negativity. So that makes the hydrogen so much stronger anion character, which is fairly unstable because hydrogen, there are many atoms, molecules around, will be very happy to take electrons away from hydrogen. So in the aluminum hydride is more like a real hydride, so it makes it more reactive. And the difference is there are many in the product. These 2 reagents give you the same product. There are many reactions give you the same product, but not always. We can see the difference. And so with the sodium boride, sodium boron compound, we can use a protonated solvent, protic solvent, which is polar, can dissolve the sodium boron hydride. But when you use a lithium aluminum hydride compound, this is a such stronger base it can react with protein solvent. So when it's used lithium compound, we cannot use alcohol or any protein environment. It has to be the polar but non-protein solvent. And the reactions, they all both give you alcohol. There's no difference. So the lithium aluminum hydride compound, we need some other solvent to do that. And okay, so this is basically we compare across. We mentioned about the hydrogenation reaction to add hydrogen to the carbonyl and produce the alcohol. We can also have there are two agents that give you hydride, add hydrogen to the carbonyl. What's the difference? The difference is, okay, this is a good example. Let's say we have a carbonyl compound with a carbon-carbon double bond. Carbon-carbon double bond. When you use a hydride reagent to add in hydrogen, the hydride is a negative charge. It will attack a positive charge in the structure. This alkene is basically electronically neutral, nonpolar group. So hydride will not react with alkene, the double bond. Hydride only react with the polar double bond, the carbonyl. So these three reagents, the first two are the hydride reaction. The hydride reaction give you, it reduce or adding hydrogen only to the carbonyl. Okay, only to the carbonyl. The carbon-carbon double bond or triple bond or whatever bond there is will not react with hydride because this bond is nonpolar. It is actually a nucleophile. It has an excess electron around. It doesn't like the extra electron from hydride. But with the hydrogenation, using metal as a catalyst, the hydrogen will add on both the carbonyl and the carbon-carbon double bond. So you can see this part being saturated. The stereochemistry, if you remember, this is a syn addition. And with the carbonyl, actually we cannot tell it is syn or anti. It must be syn. So we add hydrogen on both. That's the difference between the two kind of reagents. The hydride will reduce only the carbonyl. Hydrogenation reduce any unsaturated bond, triple or double or any kind will be reduced by the hydrogenation. And so there's some varieties of a hydride agent. And it's based on how we want the hydride agent to react to be more selective. It basically made them less like hydride. So when make the reagents less reactive, when you make the reagent less reactive, typically it is because will cause the activation energy higher, the reaction slower, and can make the reaction more selective. When you make the reagents less reactive, it can be more selective, such as we've seen in the halogenation of the carbon through the free radical reactions. The bromination, it reacts slower than the chlorination and actually giving them better selectivity. So same as those, the hydride reagents, they give us, make them less reactive and then be more selective. The way we manipulate it is the manipulation can either happens on the aluminum hydride or boron hydride. So the one that we can manipulate, those R group can be alkoxide. This has become, the alkoxide is have oxygen. Oxygen can take electron away from the aluminum or boron, and that makes the reactivity less. Cyano group also strongly pulls electrons away from the boron or aluminum, so therefore also makes the reaction makes it less reactive. And it can also get some reagents sterilely hindered. So when you have bulkier group attached on the aluminum or boron, that also limits what position can react, and also sometimes give us a good selectivity. It will only react to the place that is more open. And if somewhere the reaction site is more crowded, then those reagents will not react. So it can improve selectivity by using those less reactive agents. And the LAH, the lithium aluminum hydride, as we see, is very reactive. It can react with water. And it is so reactive, it can even react with acid or ester to give alcohol. This, in real life, in practice, we try not to use this pathway to form the alcohol. It's just because the amount of reagents we need much more reagents by doing this kind of reactions. But it's doable. So the lithium aluminum hydride can react with acid or alcohol, and the final reaction are still the same alcohol. So basically, those hydride keep adding to the position, and it can even have the substitution reaction. So the reaction pathway in next semester we'll discuss more. So far, just be aware of the lithium aluminum hydride it's more reactive. And so the reaction happens is based on nucleophilic, the nucleophilic attack, and form a tetrahedral intermediate. It can form tetrahedral intermediate. And after tetrahedral intermediate, it formed the when the reaction with ester, it actually first formed the aldehyde as reaction intermediate. It formed aldehyde as an intermediate. The aldehyde form is because tetrahedral intermediate, the lone pair form bond with existing bond, so form double bond. Same time, the alkoxide as a leaving group. So after this, you form the aldehyde. And again, aldehyde, since have carbonyl, it will react with a hydride again. So next step, eventually, one more step react. And finally give us a primary alcohol. So reaction with ester give us a primary alcohol. It's not the most efficient because you need a 2 hydride to achieve this reaction, 2 monohydride to react with 1 ester, give you final product. So this is through some practice, we kind of compare the similarity and the difference between these 2 reagents. So we look at this, is a compound has a multiple double bond. There's a double bond here, double bond here, and you have 1 more double bond. But this double bond is the alkene double bond. So the alkene double bond should not react with the hydride reaction. And so basically, what can react with these 2? That we can see this is the exercise where 2 hydride, both are hydride. So you have these 2 potentially can react because both are polar, not unsaturated bond. And so between these 2, this is a ketone. This is the ester, by the way. This is ester. This is ketone. And the sodium boron hydride would only react with aldehyde or ketone. It will not react with the ester. So the first step reaction will be happen only on this carbonyl. And if you write down the product, this becomes the alcohol. And the rest of the molecule remain the same. Okay, so that's the first product here. Okay, and after this, next step, the second step is with the lithium aluminum hydride. This is much more reactive. It can react with any kind of carbonyl group. Can be ketone, aldehyde, or ester, even carboxylic acid. So this would react with, this is actually a ester. This is actually an ester. So the hydride will first attack here. And this reaction is kind of interesting. It's maybe a little too much for our class. It first goes through the tetrahedral intermediate, and the next step, okay, if I write down the reaction mechanism, you first add a hydride here, hydride from this reagent. So add a hydride here, negative charge, and hydrogen is attached. Okay, this is come from the hydride. Oh, I think I missed something. Sorry, this is a one atom I lost. Should atom. Okay, so that's my first step. Okay, if you remember that reaction mechanism, the second step is the actual lone pair form bond. And when this coming back, the carbon need to maintain octet, so this bond breaks. And so we have a OH here. Now we have oxygen carbon double bond, and with this hydrogen. And all the other structure, all the part of the structure remain the same. The difference is we have a oxide ion formed here. So that's what happened the first step. This is still a intermediate because the carbonyl can still react with lithium aluminum hydride. So one more step. The hydride comes from the lithium. Finally, give us the alkoxide. Well, if I skip one more step, this will give us an alcohol, basically. And this will be the primary alcohol. And the other part, okay, the other part is still not being changed. And when you treat it with the water, the weak base, this will also become protonated. So that's finally the product for this reaction. First step, give us partially hydrogenated, partially reduced, and the very last step, second reaction, gives us complete reaction with the hydride, and is there are 3 locations have OH, so it's a triol, the alkene triol as a final product. So that's basically the full reduction. An example shows us how the reactivity is different among the different carbonyl groups. The carbonyl groups in the aldehyde, ketone, ester, carboxylic acid. Later we learned the carbonyl can connect with the amino group from the amide. So all these have different reactivities. The hydride, it can react with all these carbonyl groups, regardless what kind of structure. The sodium, the boron hydride only reacts with aldehyde and ketone. So that's the difference between these two. Anyway, that's my answer key for that, kind of messy. Diols. The diols are there are 2 hydroxyl groups in the molecule, and so the diols, the naming basically we focus on the location for the 2-hydroxy group. So this is the, it has 3 carbon. So the parent will be propane, and the position 1 and 3 have a 2-hydroxyl. So 1 and 3 propane diol. And this is the, when you have 6 carbons and the hydroxy group not quite symmetrical, then you need to keep the hydroxy group as low locant as possible. This is number 1. So give the OH, first OH, the lowest number. Yeah, so that's how I named that. The diol synthesis, how we make synthesis of diol. Apparently, if a molecule have 2 carbonyl groups, we can add those hydride agent or hydrogenation process to add hydrogen to those. And that's basically just just like what we learned with a single alcohol. Okay, this is the something different. It's kind of review what we learned alkene. When the 2 hydroxyl group are next to each other, Vicinal, then we have 2 ways to get the diol. Either the forming an epoxide, or use osmium or permanganate, gives a syn diol. Okay, this is an alkene reaction. The first reaction is the peroxy acids, such as the MCPBA. MCPBA basically is a peroxy acid of benzoic acid that gives us oxygen on the double bond. And once the oxygen on the double bond, that'll give you epoxide. And then later the reaction nucleophile from the water attacks the epoxide, gives diol. So basically that's what happened. And with this will give us syn diol, either osmium tetroxide or permanganate. Cold permanganate, you can keep it diol. So there's another way to give you alcohol that's a very unique and different from the others. We use a Grignard reagents. The Grignard reagents you'll see more in the next semester, because next semester we're studying the reactions of carbonyl compounds. But here we just introduce here the Grignard reagents is discovered by the French chemist Grignard. And this is one of the most powerful reagents in organic chemistry. He got a Nobel Prize because he discovered the whole series of reagents by reacting with the alkyl halides, especially bromide, with magnesium. And so this reagent, because can fairly easily adding more carbon to the structure, is basically a way to build big molecules, make it possible to build bigger molecules. And this reaction, when react with a carbonyl, can produce alcohol. So to make Grignard reagents, is typically start from a alkyl halides. It can be benzyl halides as well. They react with magnesium. It create the carbon and halides form a sort of a covalent bond, sort of ionic bond with magnesium. It's just because magnesium, it has is a metal, but it's a fairly high electron activity. So have some tendency to share electrons, not completely give away the electrons. And so the reaction produced, so for example, the bromobenzene react with magnesium give you the Grignard reagents. The Grignard reagents, you put the alkyl group to the left, magnesium in the middle, the halides to the right. So this is magnesium bromine Grignard reagents. And this one is the from propyl with chlorine, and that also gives us the propyl magnesium chlorine. So this is the alkyl group, carbon organic part with magnesium in the middle and chlorine attached on the other end. So that gives us the reagents. The Grignard reagents is very powerful reagents. It's actually very similar to hydride, because the carbon here, because bound with the magnesium, it has negative charge. So it is kind of like carbon ion being stabilized by the magnesium ion. And because it's a carbon negative charge rich in electrons, it attacked the electrophiles, such as the carbonyl carbon. And so the reaction with carbonyl, the mechanism, it goes the carbon ion come from Grignard reagents. It attacks the electron deficient positive charge carbon. And this reaction will give you the intermediate. By the way, this intermediate, it is very similar as the hydride attack on the carbonyl, very similar. The difference is an alkyl group instead of hydrogen. Okay, and also the big difference, once you form this intermediate, you can see the carbonyl compound that we started with. Now you add the alkyl group from the Grignard reagents. So this is a reaction. The product gain a carbon, gain more carbon through the reaction. And at this point, once you form this alkoxide ion, it can be easily protonated by the by water as a post-processing, and it gives us alcohol. And so you can see the reaction mechanism very similar between the Grignard and the hydride reduction on the carbonyl compounds. Very, very similar. And as the this hydride ion, by the way, this is a very strong base, very, very strong base. So any acid, any protein environment will destroy it. And the reaction produces basically a alkane and some kind of magnesium hydroxide compound. So this reagent cannot be produced or stored in the protein, such as water or alcohol or whatever such nature solvent. It has to be the aprotic environment, a polar aprotic. Because the compound is a magnesium, has positive charge. It's a polar compound. You need a polar solvent to dissolve. And very often the polar solvent we use, it is THF, tetrahydrofurane. Furane, by the way, furane is an aromatic compound, have such a structure, furane. And it is very stable. But once we have the structure adding 4 hydrogens on the double bond, we get a tetrahydrofurane. It's a very polar and a high boiling point. Very good solvent for Grignard reagents. And for course, ether. Ether is very volatile. Diethyl ether boils about 40 degrees, less than 40 degrees to make a boil. So THF is a better solvent with a slightly higher boiling point. You can use it to work with and not to worry about the evaporation and losing the solvent too quickly. And the Grignard reagents to form alcohol. Okay, this is about, we talk about the Grignard reagents. How we use for alcohol. It is Grignard reagents react with the carbonyl compound. Any carbonyl compound, in the end, will give us alcohol. So here's a ketone. A ketone reacts with the Grignard reagents. This is Grignard reagents. Okay. Ketone give us Grignard reagents. And this is the methyl in the Grignard reagent. A negative charge. It'll attack the electropositive carbon here. So you can see the final product give us a tertiary alcohol. Grignard reagents react with the ketone, give us tertiary alcohol. It can also react with the ester even. With the ester reaction, the first step is a methyl group attack on the carbon. You form the negative charge ion, and then negative charge ion coming back attack, leave, make the methyl group leave. And then once you form the aldehyde intermediate, just like hydride reaction, it will react with one more mole of the methyl Grignard reagent. So in the end, there'll be two alkyl group that come from Grignard reagent add on the carbon. So final product also gives us the tertiary alcohol. And so you can see this is how does reagent in the end. Okay, in the end, the last step, both step, you have a protonation reaction. Use water as a weak acid, give proton to the alkoxide intermediate. Finally, give us the alcohol. And so that's the reaction we have. What else we can form the alcohol? By the way, these reactions, any other reagents, if they can react with the Grignard reagent, it cannot be included in the structure. So if molecule structure in the starting material have carbonyl or carbon nitrogen, this is also very polar, unsaturated. The Grignard reagents will attack on those. Grignard reagent negative charge will attack these two carbons and give you some product that we do not want. So the Grignard reagents can give us alcohol by reacting with the carbonyl group. And they are slightly different. With ketone, it's a 1-to-1 ratio. If a reaction with ester is 2-to-1 ratio, 2-to-1 ratio, at least 2-to-1 ratio. 2 part of the Grignard reagent with 1 part of the ester. So that's the reaction, Grignard reaction.